Hello everyone, welcome to the second session of VSSP 2022. Today we have 4 speakers with us and the session chair for today is Professor Omkar Devlekar. He is currently a faculty at Azim Premji University, Bangalore. Over to you, Omkar sir.
Hi. Hello. Good afternoon, everyone. I'm very happy to be here and see many of the students from the 2022 camp handling this. And the first speaker is Priya Kaveri from IIT Madras. And her topic of presentation is covering spaces. Over to you, Priya.
Okay, good afternoon, everyone. So today we will be discussing about covering spaces. So we will start discussing why we need covering spaces. Then we will give a brief introduction to covering spaces. Then at the end, we will find the covering space of S1. Okay. So why we need covering spaces? One of the basic problems in topology is whether two objects are homeomorphic or not. That is, if we have two objects, X and Y, then whether we can find a homeomorphism between X and Y or not. So one of the smart way will be checking the topological properties of X and topological properties of Y. And if we find X satisfy some topological properties and Y doesn't satisfy some topological property, like if there is a property P which X satisfy but Y doesn't satisfy, then we can immediately say they are not homeomorphic. But does this always work? So the problem is the topological property that we know are very limited. So for example, if you are considering R2 and R3, the question is whether R2 homeomorphic to R3 or not. So if we check this compactness, connectedness, metraceability, local connectedness, etc., then what happens? R2 and R3 both are not compact, both are connected, both are metraceable, both are locally connected also. So we can conclude nothing. So we need something extra. So here is the idea of symbol connectedness. So what is symbol connectedness? Okay, a space X is said to be simply connected if every loop can be, every loop is homotopic to a point. Or in other words, just consider a space and consider any loop, any closed loop. And if any closed loop can be shrunk down to a point, we can say intuitively that is simply connected. Okay, so how can we use this notion of symbol connectedness to say whether R2 and R3 are homeomorphic? So for that, observe if we remove the origin of R2 and if we consider any loop around that origin, then it cannot be shrunk down to a point because that in the place of origin, there is a hole. But in case of R3, if we remove the origin and if we consider a loop, R3 has extra dimensions. So we can always translate that loop to the extra dimension and shrink it down. So in that way, we can conclude R2 and R3 are not homeomorphic because R2 minus origin is not simply connected, but R3 minus origin is still simply connected. But whether this works for everything, no, because if we consider torus and double torus, then this idea of symbol connectedness won't work because both are not simply connected. So we need some more generalized notion. So there is a more generalized notion of symbol connectedness, which involves certain group called fundamental group. So, okay, so we have a difficult problem that whether two objects are homeomorphic or not. To resolve it, we introduce the idea of fundamental group. Now, what can we say? If two spaces are homeomorphic, then their fundamental groups are isomorphic. So if we check the fundamental groups and if we found they are not isomorphic, then immediately we can tell the group, the spaces are not homeomorphic. But the next question will be, how will we compute the fundamental group of a given space? So the answer is computing fundamental groups of some spaces is not trivial. So we already had a difficult problem. Now we introduce the notion of fundamental group. So computing fundamental group itself is difficult for some space. So we need some extra tool to facilitate the computation of fundamental group. So here comes the importance of the notion of covering spaces. So covering space is one of the helpful tools to find the fundamental group. And covering space is also important in the study of Riemann surfaces and complex manifold. So here I will just define covering spaces and we will find the covering space of S1. We won't go to fundamental group and other things. It's just for the motivation, like why we need covering space, why it is important. That's why I explained it. Okay, so this is why we need covering spaces to find fundamental group so that we can classify the objects up to homeomorphism. Okay, so the definition, let P from E to be a continuous surjective map. The open set U of B is said to be evenly covered by P if the inverse image P inverse of U can be written as union of disjoint open set V alpha in E, such that for each alpha, the restriction of P of V alpha is a homeomorphism of V alpha onto U. Okay, what does it say? We have a continuous surjective map from E to B. Okay, now we take an open set U of B, and that open set U is said to be evenly covered by the function P. If we take the inverse image P inverse of U, then it satisfies two properties. First thing, it can be written as disjoint union of open set V alpha. And if we restrict that P to V alpha, it is a homeomorphism onto U. So we have this figure. Okay. So this is our U. This is our U. And this thing is P inverse of U. So what we have, this P inverse of U is disjoint union of V alpha. So suppose it is V alpha I and it is V alpha J and something. And this V alpha I, if when we restrict P to this V alpha I, it is homeomorphic to U. So these V alphas and U will look alike. Okay. So this is the figure. Every V alpha will be of the same size and shape of U. Then we say that U is evenly covered by P. Okay. 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 And the collection V alpha will be called the partition of P inverse of U in slices. So these each V alpha, it is called a slice. So I hope the definition is clear. Now we have another definition, that is what is called a covering map. Now we said when a set U is called evenly covered by P. Now we define what is a covering map. So P from E to B continuous surjective map. For given any point B in B, if it has a neighborhood that is evenly covered by P, then P is called covering map. That is, given any point B in B, if we can find some UB such that UB is evenly covered by P, it means P inverse of UB can be written as disjoint union of V alpha. And if we restrict that P to each V alpha, it is homeomorphic to this U alpha. Then P is called covering map, and the set E, the domain is said to be covering space of B. That is the codomain. Okay. Now there is a remark. For each B in B, the subspace P inverse B of E has discrete topology. I mean, under the subspace topology, the topology will be discrete. The remark 2, if P from E to B is a covering map, then P is an open map. That is, P will take open set to open set. So these are just remark. You can try to prove this. We won't use this in our proof. This is the extra condition that this covering map satisfies. Now, an example of covering map. This is the most trivial example. Just take X to be any space and take identity map I from X to X. Then I is a covering map. Why? What we have to check? For each point, we need a neighborhood which is evenly covered by P. So take any point, take any neighborhood. Here we can take any neighborhood. Then inverse image of that neighborhood will be that itself. If you take B and consider some neighborhood UB, then I inverse of UB will be UB itself. So that collection V alpha here, it will be singleton UB. Okay, so this identity map, it's like a trivial example. So I is a covering map. Now we will go to some non-trivial example, that is the covering space of S1. So here we will prove the map P from R to S1 given by the equation P of X equal to cos 2 pi X sin 2 pi X is a covering map. Okay, so we have to prove it is a covering map. So what we have to show? In order to prove P is a covering map, given any point AB in S1, we need to find a neighborhood U of AB such that P inverse of U can be written as disjoint union of V alphas, and the other condition, restriction should be homeomorphism. So first we will concentrate on this. So suppose AB in S1 is in the first or fourth quadrant. So first I'm proving it for AB in the first or fourth quadrant. That is, AB is lying in the right side. Okay. Now I have to find a subset U consisting AB, right? So what U I am choosing? This U I am choosing. In this figure, you can see that U, they have marked this semicircle on the right side. Okay, that U I am choosing. So what is that? How we can describe that U? That U will be the subset, that U will be subset of x1, and it consists those points for which cos 2 pi x is positive. That is, every point in S1 we can write it as cos 2 pi x and sin 2 pi x. So since it is on the right side, the first coordinate will be positive. So I consider that subset U of those points in which cos 2 pi x is positive. Okay. Now what I have to show? U we got. Now we have to find what is P inverse of U. So P inverse of U is precisely those x in R such that cos 2 pi x is positive, right? So now we have to find those x where cos 2 pi x is positive. So we know cos is positive on this interval minus pi by 2 plus 2 pi n, comma pi by 2 plus 2 pi n. So where cos 2 pi x will be positive, we can just divide the length of interval by 2 pi. So cos 2 pi x will be positive on n minus 1 by 4 to n plus 1 by 4. So P inverse of U is what? Just x such that cos 2 pi x is positive. So P inverse U is precisely the union of n minus 1 by 4 times, n minus 1 by 4 comma n plus 1 by 4, where n is in n. And these each of these set is disjoint. So we can write P inverse U as disjoint union of this interval, and we call it as Vn. So this is our U. I'm taking AB in the first or fourth quadrant. So we choose this U, and this Vn will look like this. V0 will be minus 1 by 4, and others we can write. And clearly this is disjoint. Okay. Now what else we need to prove? Now we got P inverse U as a disjoint union of Vn's. Now we have to prove the restriction is a homeomorphism to U. So how will we prove that? So to prove something is a homeomorphism, what all things we need? We have to show that it is a bijective map, it is continuous, and inverse is also continuous. So it's already given P is continuous, so its restriction is also continuous. Now I have to show this is injective, surjective, and inverse is also continuous. So we will do we will prove it smartly, because what we will do is we won't prove Vn to U it is a homeomorphism. Rather, we will prove Vn bar to Vn bar it is a homeomorphism. So how we will prove? Restrict to any, if we restrict P to any closed interval Vn bar, then P is injective. Why? Because sine 2 pi x is strictly monotone. Vn bar is what? Closed interval n minus 1 by 4, n plus 1 by 4. There sine 2 pi x is strictly monotone. Why? Its derivative cos 2 pi x is strictly monotone. Its derivative cos 2 pi x strictly positive. So sine 2 pi x is strictly monotone. So that one component is strictly monotone. So it is clearly injective. P is clearly injective. Now we have to prove it is surjective. That is, from Vn bar to U bar, it is surjective. So how will we prove that? We have to use intermediate value property of sine 2 pi x. Okay, that I will write here. So what we have is Vn bar is n minus 1 by 4 to n plus 1 by 4. I have U bar here. Now I have to prove this is surjective. That is, take an element AB in U bar. I hope it is visible. Hello?
Yes.
Okay, thank you. So what I have to show, I have to find x in Vn bar such that A comma B is precisely cos 2 pi x comma sine 2 pi x. Okay. Now, how will we show that? See, consider this interval. Okay, AB is in U bar, right? So So it belongs to circle. So we know that a square plus b square equal to 1, which will show that where does b belongs to. B is belongs to minus 1 comma 1. Oh, just see, u is what? U is this interval. Okay, my drawing is bad. Use this semicircle. Here, b will, second coordinate will go to minus 1 to 1. Okay, now we can observe sine 2 pi of n minus 1 by 4 is minus 1, and sine 2 pi of n plus 1 by 4 is 1. Okay, now we are taking b here. So what we can say, this b actually lies between sine 2 pi n minus 1 by 4, since it is minus 1, less than b, less than. Okay, now by intermediate value property, sine is continuous on this Vn bar. There exists some x in Vn bar such that sine 2 pi x equal to b. Right? Now what is a? A is just root of 1 minus b square. Why it is positive root? Because we are considering u here. Here a will be positive. Now substituting b to be sine 2 pi x, we will get a to be cos 2 pi x. So this x will work. So we got x in Vn prime such that a comma b equal to cos 2 pi x sine 2 pi x. Okay. So this will show that that map is surjective. Okay. So what we used here, we used the intermediate value property of sine 2 pi x. So we got P is injective from Vn bar to U bar, Vn is surjective, and P is also continuous because restriction is always continuous. A restriction of continuous map is always continuous. Now we have to prove inverse is continuous. So for that, what we do, we know that a continuous bijective map from a compact space to Hausdorff space is a homeomorphism. So here Vn bar is compact and U bar is subset of R2. So under it is also Hausdorff. So we can apply that theorem here. So we have continuity and bijectivity. So we got P restricted to Vn bar is a homeomorphism directly from the result. Now what we need actually, P is a homeomorphism from Vn to U. But what we got now, it is a homeomorphism from Vn bar to U bar. So how will we show that P restricted to Vn is a homeomorphism onto U? That's a simple observation, because here n points of Vn bar is actually mapping to n points of U bar, right? Because n points of Vn bar is n minus 1 by 4, n plus 1 by 4. And it is mapping to where 0 comma minus 1 and 0 comma 1. So if we remove that both points in from Vn bar and U bar, we'll get Vn and Un, and it will be a homeomorphism. Or you can use that restriction will be a homeomorphism and all. If you restrict P to Vn, and it will be homeomorphism onto its image. That also you can use. Or by just observing the endpoints of Vn bar is mapping to endpoints of U bar. So if we remove the endpoints, still it will be homeomorphism. So we got P is a homeomorphism from Vn to U. So first we wrote P inverse of U as disjoint union of Vn's. And now we proved P restricted to Vn is a homeomorphism with with U. So we can now at the point AB, now we got the result. Now what if AB is in some other quadrant? We can argue in similar way. Similarly, for other points, we have to change U accordingly. Then we will get this homeomorphism. So we will get the homeomorphism and we can prove it is a covering map. So hence we conclude P is a covering map. Okay. So now the exercise is justify the second last line of the proof. That is, similarly for other points of the circle, we can argue in the same way. How we can argue? We have to change the U. That is the idea. Here we took AB here. So we took this U. Now if AB is somewhere else, what you should take, that you can think. So that is an exercise. Okay, so this is the covering map. Okay, this P is a covering map that we proved. Now, why we proved this? This will be helpful to find the fundamental group of S1. So if we got fundamental group of S1, then we can have more result. Like we can say whether S1 is homeomorphic to some other space or not, because S1's fundamental group we know, and if we know fundamental group of some other objects, and if they are not isomorphic, immediately we can say they are not homeomorphic. Okay, so that is why this result is very important. Yeah, that is it. So the reference is Monk's topology that you can see in that part 3 algebraic topology will be the. They will start from homotopy, fundamental group, everything. I just took covering spaces. That's it. Thank you.
Thank you, Kaveri. It was a good presentation. Any questions or remarks? Okay. So Kaveri, if you can go to the second slide where you were talking about the remarks.
Remarks?
Remarks of, yes, about the covering map. Can you quickly tell us about the remark 1? How would the proof go?
So the thing is, like, we have to show that if we take B in B, the subspace B inverse of B has discrete topology. So for showing discrete topology, we have to show every point is a closed set. That will be enough.
Yes.
Okay, so how we will argue is P inverse of B. Okay, since it is given, it is a covering map. For B, we will find a neighborhood UB such that UB is evenly covered. Right? So P inverse, that is P inverse of UB can be written as disjoint union of V alphas. So this P inverse of B will precisely belong to one V alpha, since that is a disjoint union.
Yes.
Now we will use, it is a home. Now if we show that this P inverse of B intersection, that V alpha is a singleton point, then we are done.
Yes.
So,
so you actually proved that the singletons are open.
Yeah, sorry, singletons are open, not closed, sorry.
Yeah, no, that can also be done.
Yeah, but here it will be easy because V alphas are open.
Yes.
And that will be single point because P from V alpha to U is a homeomorphism. So that should be single point.
Yes.
Yeah.
Okay. Any other comments from anyone? Okay. So thank you, Kaveri. It was a good presentation.